long time ago, in the late 17th century, Isaac Newton asked a question: if we have some number of objects all bound to each other by gravity, how do these objects move around each other? Well, let's start with an example. Let's say we have a planet, like the Earth, and we have a moon. How do these objects move around each other? Well, as you can guess, the moon would orbit around the Earth in a circle, or more accurately, around the center of masses. And this, in fact, this orbiting around their centers of mass is actually the general solution to this problem when we are only dealing with two bodies. But in real life, we often have more than two objects. So let's add one more object. Now, how do these three objects move around each other?
Well, it would be like around their center of mass too, right? Same case.
We actually don't have a general solution for this. In fact, we believe there isn't an analytical solution. This problem is surprisingly difficult, and it has its own name, the three-body problem to be exact. Very creative, right? So allow me to write this out mathematically to get my point across. The three-body problem looks a little something like this. So we have R, denoted position, and if you're a physics person, you'll know that if you take the first derivative of R, you have the velocity. If you take the second derivative, you have acceleration. So that's it. So, as you can see, it's a system of second-order ordinary differential equations. And we should actually note that these R's are actually three-dimensional vectors because we live in three-dimensional space. So this is actually a system of 9 ordinary differential equations. Very difficult. Luckily, we have some particular solutions for specific cases. So let's talk about one set of them today. Let's say you have one relatively massive body, like a star or a planet, and you have a relatively smaller body, such as a moon or a planet, and we want to place a third object in a place such that it follows the middle-sized object in its orbit around the larger object. Where can we place this object such that we can accomplish that?
Well, I would think somewhere in between the two, right? Would that work?
That'd actually be correct. There actually is one point right in the middle where the gravities cancel out from these two objects where we can do that. And in fact, there are 4 more cases where this happens. These 5 points in total are known as the Lagrange points and were discovered by Leonard Euler and Joseph Louis Lagrange in the late 18th century. Euler discovered 3 points, L1 here, L2 here, and L3 here, all lying along the line of the larger masses. However, these points are unfortunately unstable. If you try to put something at any one of these 3 points, over time it will eventually fall out of that point and into orbit around one of these objects, unless you make constant adjustments. Lagrange, however, managed to find 2 more points. He found L4 and L5 here. And at these points, you actually have a stable position. And if you place an object at L4 or L5, that object will actually stay there. And in fact, in the 20th century, we looked at the L4 and L5 Lagrange points for various celestial bodies, including Jupiter, and we found many natural objects sitting at those points. The asteroids at Jupiter's L4 and L5 points are now known as Trojans. So, As you can see, the three-body problem is a very relevant problem in astronomy and astrophysics. Our future understanding of systems in space would be reliant on solutions to the three-body problem.